Okay, today's lesson is a continuation. It's day 2 of the section 9192. It's just the introduction to sequences and series. You can't do series until you can do sequences, because series are sums of sequences of numbers. So basically a sequence is a list of numbers. Let's recap. So sequence It's a list of numbers, and it has a pattern which can be given explicitly or recursively, and then a series is a sum of numbers. Well, they also have a pattern. So basically, you take a sequence and you sum up all the terms, and that's a series. Alright, so where we got to on the last lesson, we were talking about how with oscillating behavior, sometimes oscillating behavior would converge and sometimes would diverge. Well, that's the next step. Next step is if we look at any pattern, can we decide if that list of numbers is going to converge or diverge? So our next step is, hang on, does sequence converge or diverge? Well, let's look at an example. This is our first example. If we have some sequence where each number, the nth, so the n going to the nth term, each term is the natural log of whatever term it's at, so it's the first term, second term, third term, fourth term, over n. And we want to know, does it converge or diverge? Well, basically what we want to know is, if it converges, it means that the nth term, when I go to infinity, that's a number and not just infinity or negative infinity. So what does it look like when we're going to infinity and negative infinity? Isn't that a limit? So the way we're going to evaluate this is we're going to take the limit as n goes to infinity of the natural log of n over n. And we know that from the graph, so if we look at natural log of n, where the x-axis is the n, you know the graph does this. So as we approach 0, we go to negative infinity. As we go to infinity, we approach infinity. So we know that this first term, or the top of the term, is going to go to infinity. Well, the bottom's also going to infinity. And what did we do when we had something where the top, the numerator and the denominator were both going to infinity or negative infinity? We had something that we could apply L'Hopital's rule to. So L'Hopital's rule says that if we take the derivative of the top and bottom, we can take the limit as n goes to infinity. It equals the original limit. So the derivative of natural log of n is 1 over n. So we've taken the derivative of the numerator. Then we take the derivative separately of the denominator. Derivative of n is 1. And as n goes to infinity, as this goes to infinity, the whole thing goes to 0, and the limit exists. So if the limit exists, then that sequence converges. So therefore, the sequence converges because the limit as n goes to infinity, as we have an infinite number of terms of a subscript n, exists. And that's our answer. And it's how it's supported. Alright, well, this is why we needed L'Hopital's rule. This is why we need to understand limits. For our next example, before we start it, I need to talk about factorials. which you may or may not have seen. You should have seen in Algebra 2. You should have seen again in Pre-Cal, I think. But let's go over it. So suppose you see 6, a very excited 6. It's 6 for the exclamation point. Well, that's a factorial. And what that means is 6 is so excited that 6 is going to multiply itself times 5, and then times 4, and then times 3, and then times 2, and then times 1. What happens is, if it's 6 factorial, you're going to multiply 6 by every integer going from 6 to 1. If it is n factorial, it is going to be n times n minus 1. I'll get rid of that since it's parentheses. And then times n minus 2, and then times n minus 3, dot, 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 all the way to 1. That's by definition. Alright, one other thing. Just so you know, 0 factorial is 1. By definition. And it's a pattern thing. If you look at, if I do n and then n factorial, and I leave a spot for 0, we won't do 0 first. But if we do 1, it's 1. If we do 2, it's 2. If we do 3, it is 3 times 2 is 6. If we do 4, it's 4 times 3, it's 4 times 6 essentially, which is 24. If we do 5, it's 5 times 24. Put it there, put it there, so it's 120. And you keep going, right? And the whole point is, it's a matter of, it's doing patterns. So, the only way to get 1 factorial, if you go back to 0, is that the 0 factorial has to be 1. Because otherwise, I'm trying to remember, how did that pattern work? Anyway, I'll come back to this. But anyway, there's a way in this pattern that 0 factorial has to be 1. But by definition it is. And I'm trying to remember why I could explain it to you. I think that's the pattern. I will look at it again to make sure. But basically based on patterns, 0 factorial has to be 1. Alright, why did I go through that? Well, we need factorials when we do series because we are going to represent all those transcendental functions, natural log, exponential, sine, cosine, tangent, inverse. We're going to represent those as the summation of polynomial terms, which means we're going to get into series, which means we're going to add up things where we're going to have factorials. So we need to understand how to handle those. So if, let me go to the next page. For our second example, we're going to say that our sequence is defined based on a factorial. So the question is, does the sequence converge? In the sequence, we're going to have a term defined, the nth term defined as n plus 1 factorial over n plus 3 factorial. And the question, does that converge or not? Well, we have to take the limit of this, but we should, well, we'll go ahead and do it all at once. So I'm going to take the limit, oops, try to write a fraction before I need to, of n going to infinity, and we're going to write out that factorial. So the top factorial is going to be n plus 1 times n minus 1 times n minus 2 dot 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 all the way to 1 over, and for n plus 3 it's going to be n plus 3 times n plus 2 times n plus 1 dot 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 all the way to 1. And what you see is that this n plus 1 matches up to this. All these three, they match up to the dot dot dot, and the 1 matches up, and then those dot dot dots match up. And all that's left over is the n plus 3 and the n plus 2. So this becomes the limit as n approaches infinity of 1 over n plus 3 over n plus 2. Well, as n goes to infinity, that whole fraction is going to go to 0 because you're dividing by infinity. Since it goes to 0, the limit exists. Since the limit exists, the sequence converges. So therefore, the sequence converges because the limit as n goes to infinity of a subscript n exists. And this is how you will justify your answer on a free response question. Now, this standalone will not be the question. What it is this will be the justification for something else. So in order to justify that your sequence is converging, you first have to show that the series converges because the sequence converges. That's just because a sequence converges doesn't mean the series converges, but a series can't converge if the sequence doesn't converge. So your first check on series is always, if the sequence doesn't converge, the series doesn't converge, and you just stop. So that's always our first test, and so that you actually are on track to begin chapter 10 already. Alright, so once we've done that, that's it on sequences. It's just laying the groundwork for our series, which is what we need to do. So now we're going to talk about series. And the most important kind of series, the finite series are not so interesting. That's not what calculus is all about. Calculus is all about the infinite. So infinite series Alright, for an infinite series, it's the sum of an infinite number of terms. In a sequence. Because on series we define them. Now, it doesn't mean that you can't add up a bunch of numbers, random numbers, but specifically we are talking about things that have a pattern that we can follow. All right, a partial sum, where it means we're going to add up a few of the terms. So we'll pick some in 10, 20, 100, a million. So for instance, the 10th partial sum is the sum of the first 10 terms. So it's the sum of the first plus the sum of it's the first plus the second term plus the third term plus the fourth term plus ... all the way to the nth term, whatever that is. So if I want the first partial sum, it is the first term. If I want the second, that was really messy, second partial sum, I need the first term plus the second term. If I want the third partial sum, it is the first term plus the second term plus the third term. And you just keep going. Now, for infinite series, it would be an infinite number of terms, and we don't want to write out that many, and we don't want to do ... every time. So we have a notation, and you've already seen it when we did Riemann sums. So infinite series that's going to be the summation of n equal 1 to infinity. So I'm starting at 1 and going to infinity of whatever pattern I'm using for my terms. So it means that it is a1 plus a2 plus a3 plus ... to the nth term, which is an infinite term. But the notation, we're just going to use the summation notation. You just need to know what it means. Okay, so what does that mean for us? That means that now that we can write these down, we can see if these converge. Because if they converge, and we can represent one of our transcendental functions as a series that converges, then we can find the value of one of the transcendental functions. Is basically what it boils down to. So for our first example, we are going to see if the series, so does the series n equals 1 to infinity of 2n plus 1 converge. And so we look at it and we go, okay, well, what does that series look like? Let's just look at it. So we have the summation of n equals 1 to infinity of 2n plus 1. Well, that's going to equal 2n plus 1. Well, actually, let's go ahead and put in 1. So that's going to be 3. And we put in 2, it's 4 plus 1 is 5. And if you look at this, is this a line that has a y-intercept of 1 and a slope of 2? Well, so that means that every time I increase my n by 1, I'm going to increase my y, my output, by 2. So it's just the odd numbers, starting at 3. And it's going to keep going, and it's eventually going to get to infinity. Well, is there any chance that this is going to converge if I'm adding up all these numbers and they keep getting bigger and they're approaching infinity? It's not going to be, the limit's not going to exist. So basically, I can say the limit as n goes to infinity of 2n plus 1, this is checking this is the sequence check. Since that goes to infinity, so the limit doesn't exist, then there's no way the series where I'm adding up those is going to converge. So since the series doesn't converge, the series doesn't converge because the sequence doesn't converge. So let me write that down. So basically, where we got to was neither, actually I'm not going to say that, so since the sequence doesn't converge, because the limit as n approaches infinity of a subscript n does not exist, then the series doesn't converge. And that's our answer. Okay, so from this we get an important concept. It's basically that if the sequence doesn't converge, then the series can't converge. So one of the things we want to write down is that the summation as n equals 1, and you're just going to give me a moment. Let me write it down and then I'll explain. So I have some series that is composed of adding up all the terms of a sequence that's defined by the pattern a sub n. Well, if I look at this in terms of partial sums, I can look at each term. So there's the first term, and then there's the sum of the first 2 terms, and the sum of the first 3 terms, and I can keep adding a term to it. If that summation, if the limit as the number of terms goes to infinity of the partial sum, if that equals some value L, then the series converges. To that value L. So up above in our other one, the sequence did not converge. It wasn't going to a particular value, so I couldn't add up all the values and get to a partial sum that was converging because I kept adding bigger and bigger terms. So there's one check we can do. If the sequence diverges, meaning the list of numbers goes to infinity or negative infinity, then there's no way the series is converging, so we just say it diverges. And then the next thing we can do is, once we know that the list of numbers converges, then we can look at the series and go look at the partial sums and go, okay, if we're starting adding up terms, can we see a pattern in them so that we know it's going to converge to a value? And that's the next way we do this. So we have an example. This is our example 2. I want to know, does the summation of n equals 1 to infinity of 3 over 2 to the n power converge? Well, we can look at that and go, okay, what's the, real quick, first thing we do, we're going to check, does the limit as n goes to infinity of 3 over 2n converge? What's it equal? Well, if you look at this, the bottom's going to infinity, so the whole thing's going to equal 0 because you're dividing by infinity. So therefore, limit exists. Since the limit exists, the sequence converges, right? So sequence converges. Since the sequence converges, now I'm going to look and see, can I see a pattern with the partial sums? So we go to our partial sums, and we start off and we go, okay, the first partial sum is going to be if I put in a 1 in there. But before I get carried away, I'm just going to write this out. So the summation of n equals 1 to infinity of 3 over 2n is going to equal 3 over 2 plus 3 over 2 squared, which is 4, plus 3 over 2 cubed, which is 8, plus 3 over 2 to the 4th, which is 16, plus dot, 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 all the way to 3 over 2 to the n, right? So my first partial sum is going to be the 3/2. My second partial sum is going to be 3/2 plus 3/4. Well, that's 1.5, and I'm adding a 3/4. That means I get 2.25. And then my third term, I'm going to add in 3/8, and I'm going to get 2.625. And if I look at the fourth partial sum, I'm going to get 2.815. Does it look like we're approaching a value? Well, let's keep going all the way to the 10th term. What about the 10th partial sum? The 10th partial sum, if I end up the first 10 terms, it's 2.997. What does it look like it's converging to? It looks to me like it's going to a value of 3. And it just so happens that's what it is. So therefore, the summation of n equals 1 to infinity of 3 over 2 to the n power is equal to 3, and that series converges. So what do we say? What do we justify it with? We say the series converges to a value of 3 because the limit as n approaches infinity of the partial sum, meaning as I add another term and another term, each time I add another term till I get to an infinite number of terms, I'm going to be adding something that's smaller and smaller and smaller, and the sum is going to approach 3. So I just have to say that this exists. Okay, all right, the last thing I want to do is I want to leave you with some factorial problems to try. So what I'm going to do is I'm going to write them down. You're going to pause this, try to do them, and then start back up the video and listen to my explanation of how to do them. So the first one you're going to do is going to be n plus 1 factorial divided by n factorial. All I want you to do is simplify that. So my second one is also just to simplify. You're going to do 2n minus 1 factorial over 2n plus 1 factorial. And then you're going to do 3, which is the limit. Now we're going to take a limit as n approaches infinity of n plus 1 factorial and then 4, we're going to do the limit. Yeah, that's messy. Limit as n approaches infinity of Oh, hang on. That last one was supposed to be over n factorial. There we go. And the fourth one is going to be n minus 2 factorial over n factorial. All right, so you're going to pause the video and try these, and then we're going to talk about them. All right, I'm going to go ahead and talk about them. So on the top one, when I simplify this, remember, factorial means you take that number and you're going to subtract 1 from it. You're going to multiply it. Starting there, you're going to go to each one of the integers going down from it. So you're going to subtract 1 from it each time. So on this one, I got n plus 1. That's my first term. So I got n plus 1, and then my second term is going to be subtract 1 from that, so it's going to be n. My next current term is going to be n minus 1, and then I'm going to go to n minus 2, and then I'm going to keep going all the way down to 1. All over n factorial, which starts at n. Then my next term is going to be n minus 1, then n minus 2, dot, 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 all the way to 1. And if you look at this, when you start canceling out the terms, everything's going to cancel out except for an n plus 1. Now, when you do the next one, it's a little trickier. So you start with 2n minus 1, and you're going to keep subtracting 1 from that, whatever that number is. So you have the 2n minus 1 is my first term, and then my next term is 2n, and for that whole number, that represents a number, and we're going to subtract 1 from it each time to go down. So that means it's 2n minus 2, and then it's 2n minus 3, all the way down to 1. Oops, only need 3 dots. And then for the top one, that's the top one. The bottom one, we got 2n plus 1 times 2n times 2n minus 1. Oh, look, now we got it, 2n minus 2, dot, 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 all the way down to 1. What happens is these terms cancel out, and you're left over with 1 over 2n plus 1 times 2n. For our next one, we actually want to take the limit. So first, we're going to write it out, and then we're going to simplify it, and then we're going to take the limit. So it's going to be n plus 1 times n minus 1, dot, 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 down to 1. And on the bottom, I'm going to have an n times n minus 1, dot, 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 all the way to 1. And the n minus 1 all the way down is going to cancel out, and I'm going to end up with the limit as n goes to infinity of n plus 1, which is infinity plus 1, which means it goes to infinity, which means it doesn't exist, so it doesn't converge. For my last one, I'm going to end up with n minus 2 on top, and then it's going to be minus 3, and then n minus 4, and then n minus 5, right? All the way down to 1. Whereas on the bottom, I start at n, and then I get n minus 1, then I get n minus 2, and n minus 3, and dot, 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 all the way to 1. The n minus 2 cancels out, the n minus 3, then it's 4. Everything's going to cancel out except for, I'm going to end up with, oops, and I forgot to write a limit. Limit as n goes to infinity, so I get limit, that is n goes to infinity, of 1 over n times n minus 1, which that's going to go to 0, so the limit exists. And if this was checking on a sequence, we would say the sequence converges. If we're checking on a series and a sequence, So in 3, both diverge. If the sequence doesn't converge, then the series can't converge. Whereas in 4, the sequence converges and maybe the series converges. Okay, so that's it for the lesson for today.